Dear students, welcome to second PUC physics class, that is moving charges and magnetism. Today let us see Ampere's Circuital Law. So in the last video we have seen Biot-Savart's law and the expression for magnetic field at a point along the axis of a circular loop. So today let us discuss about Ampere's Circuital Law. What is this Ampere's Circuital Law? The statement is like this. The statement of Ampere's Circuital Law is like this. The line integral of B dot dl of or for a closed curve is mu naught times the current I through the area bounded by the curve. So this is the statement of Ampere's Circuital Law. According to Ampere's Circuital Law, the line integral B dot dl for a closed curve is mu naught times. What is mu naught? Mu naught is the permeability of free space, right? The current I through the area bounded by the curve. So let us see what is the meaning of line integral and the closed line integral. It is like this: integration with a circle, then it means that this is closed integral. So closed line integral is represented by this symbol. Okay. Now let us see what is the meaning of line integral and closed line integral. So for that, consider one path. You just imagine that this is a path AB. So there is a particle. So this is one particle P. Okay. So in order to move this particle from here to here, or to displace this particle from here to here, what we have to do? We have to apply some external force. So this is the direction of external force. In this direction we are applying force. So this is F vector. So the object displaces. So this is the initial point, and the object, after the application of force, you just imagine that the object comes here or it moves here. So this is nothing but the displacement is dr. So displacement is a vector quantity, so dr vector. We know that the dot product between F vector and dr vector is nothing but the work, right? So work or dw is equal to force into displacement, or we can easily calculate the work done by the force in moving the particle from here to here. How much work is done? So this is dw. So this small work is represented as dw, right? Similarly, we are applying force in order to move the object from here to here. We get dw. So like this, we are applying force on the object and the finally object reaches the point B. So from A to B. So now we have to calculate what is the total work done in moving the object from A to B. What we have to do? So, the total work done W is equal to integration of dW. Integrating all the dW's, we get the total work done in moving the object from A to B. So, the lower limit is A, upper limit is B. So, this is line integral. What is the meaning of this? Closed line integral. So, closed line integral is represented by this symbol. So, closed line integral means if the path is closed, if the path is like this. So, the initial point is A, final point is also A. If the path is closed, then we write closed line integral. So, this is the symbol. From A to A, no need to write from A to A. So, this is enough. So, total work done is nothing but closed line integral of dW, or W is equal to closed line integral of F dot dr, right. On integrating all the dW's, we get the total work done over this closed loop. So, this is the meaning of closed line integral. Okay. So, the line integral or closed line integral, that is closed line integral B vector dot dl vector is mu naught times the current I through the area bounded by the curve. What is this B and dl? We know that dl is a line element, B is the magnetic field. So, consider a conductor which is carrying current I in this direction. So, current is flowing in this direction. So, I, we know that when current flows through the conductor, around the space we have magnetic field, because the source of this magnetic field is nothing but the electric current. So, the magnetic field or the magnetic field lines are like this. So, we get when current flows through the conductor, around the space we have magnetic field lines, and we get circular magnetic field lines, because magnetic field lines are always closed or they form closed loops. So, magnetic field lines are always closed lines. So, like this, in this pattern we have the magnetic field lines, or the magnetic field lines are generated like this around the conductor. Okay. So, how to give the direction of magnetic field? We know that we can use right hand thumb rule. If the conductor is like this or current flowing through the conductor is like this, then thumb gives the direction of current and curled fingers or all other fingers give the direction of magnetic field, or if all other fingers give the direction of current, then the thumb gives the direction of magnetic field. If the current is flowing in downward direction, then you have to keep your hand like this. Okay, this is the direction of current and all other fingers give the direction of magnetic field. So, now let us see at this point what is the magnetic field. So, this is a closed curve. Let us consider this curve. So, this is also closed. So, this curve is also closed. Okay. So, this is nothing but the closed curve. I will consider this curve and I will consider a point P on the curve. So, this point P is at a distance r from the conductor or from the axis of the conductor. So, r is the distance between conductor and the point P. Okay. If I consider a point P here, then this is the distance from the conductor to the point P. Both are equal. If I consider a point here, so this is r. So, if I consider a point here, this is r. If r is constant, you just imagine that this is a conductor Okay. So, this is a conductor, this is a closed curve. So, at every point the conductor is, or the distance from the conductor to the point is same. So, R is same. So, this is the point P. At this point, what is the magnetic field? Or if I consider the point here, point P, then this is the direction of magnetic field. Magnetic field is a vector quantity, so this is the direction of magnetic field. We know that dl is the line element, which is also a vector quantity. So, this is the direction of dl. dl and B, they are in the same direction. So, the angle between BL vector and DL vector is 0. So, theta is equal to 0. If I consider a point here, how to draw the direction of magnetic field? In order to get the direction of magnetic field, you have to draw one tangent at the point. So, if you want to calculate the direction of magnetic field here, then you have to draw one tangent here. So, this gives the direction of magnetic field. What is the direction of dl? dl is also in the same direction. Here also angle between B and dl is 0. Since all the points are at same distance from the axis of the conductor, magnitude of magnetic field is same. Magnitude of magnetic field remains constant because they are at same distance from the conductor, because R is constant. If R is constant, then the magnitude of magnetic field is also constant. Direction is not constant. In order to get the direction, you have to draw one tangent at the point. So, that tangent will give you the direction of magnetic field at that point. So, if you want to find out the direction of magnetic field here, then you have to draw one tangent here. So, this is the direction of B and this is the direction of dl, again dl vector and B vector. So, at every point angle between B vector and dl vector is 0. So, from this expression, closed line integral B vector dot dl vector is equal to dot product between these two vectors, A vector dot B vector is equal to AB cos theta. Here we get B vector dot dl vector, that is B dl cos theta. What is theta there? Theta is the angle between B vector and dl vector. B vector and dl vector. So, in this example, angle between B vector and dl vector is 0. So, cos 0 is equal to 1. So, closed line integral B vector dot dl vector is equal to B into dl. B is nothing but the magnitude of magnetic field. So, magnitude of magnetic field is constant in this example. Integration of dl. What is dl? dl is a infinitely small line element dl. So, this is dl. So, the integration of dl gives you the circumference of the circle, or this whole loop is nothing but the integration of all the line elements. So, integration of dl is nothing but this whole loop. So, this is nothing but the circumference of the circle. If r is the radius, then circumference of the circle is nothing but 2 pi into r. So, this is about this law. So, according to this law, the line integral B vector dot dl vector is equal to mu naught times the current I through the area bounded by the curve. if you are considering this curve, then I is the current flowing through this conductor. Okay. So, the conductor should be enclosed within that curve. So, B vector dot dl vector is equal to mu naught into I. So, this is Ampere's circuital law, where mu naught is the permeability of free space, I is the current enclosed in the area or the curve, B is the magnetic field, dl is the line element. So, I will write B is the strength of the magnetic field, dl is the line element, mu naught is the permeability, of free space, I is the current flowing through the conductor, which is enclosed by the curve. Through the conductor. And theta is the angle between magnetic field and the line element. Because B vector dot dl vector is nothing but B dl cos theta. So, B dl cos theta is equal to mu naught into I. Okay. Dot product between B vector and dl vector for the loop or the curve is equal to mu naught times the current through this conductor. So, this is Ampere's circuital law. Now, let us see, using this Ampere's circuital law, how to derive an equation for magnetic field due to a straight current carrying conductor at a point P outside the conductor. So, for that we have to consider one conductor. So, you just imagine that this is a conductor which is carrying current I. So, I is a current flowing through this conductor in this direction. So, in the upward direction the current is flowing through this conductor. So, this is nothing but the area of cross section. So, this is the area of cross section. So, this is also area of, this is the area of cross section. So, this is the axis of the conductor. So, this is the axis and this is the radius. Let A be the radius of the conductor. So, this is A or this is A. A be the radius of the wire or radius of the conductor. I is the current flowing through the conductor. In this direction current is flowing. So, let I be the current flowing through this conductor. When current flows through the conductor, we know that around the space we have magnetic field lines. So, this is the magnetic field line or the magnetic field. So, this is the magnetic field which is created around the conductor. Now, we have to calculate the magnetic field at a point due to this current carrying conductor outside the conductor. So, let us consider a point P outside the conductor. Okay. So, this is the point P which is in this curve, and this point P is outside the conductor. Now, let us see what is the expression for magnetic field at a point P due to this I. Let R be the distance from the axis to the point P. A is the radius of the wire. So, consider a current carrying conductor, or consider a conductor with radius A. A is the radius of the conductor. Let I be the current through the conductor and R be the distance between the point P and the conductor, or from axis of the conductor. R is the distance, A is the radius, and I is the current. Let us use Ampere's Circuital Law. According to Ampere's Circuital Law, closed line integral of B vector and dl vector, B vector dot dl vector is equal to mu naught into I. So, B dot dl is B dl cos theta, which is equal to mu naught into I. We know that. So, R is same for all the points. If you consider another point P in this loop, then also the distance R is same. If I consider the point here, R is same. So, for this loop, R is constant. If R is constant, then that means magnitude of magnetic field is constant. So, I will take the constant outside the integral. So, B theta is 0, angle between B vector and dl vector is 0. So, cos 0 is theta is equal to 0, cos 0 is equal to 1, and the remaining is dl, which is equal to mu naught into I. So, B into line integral, closed line integral of dl. So, dl is the small line element. So, this is dl, this is also dl, this is also dl. On integrating all the dl's together, we get this loop. So, integration of dl is nothing but circumference of the circle. So, circumference of the circle is, we know that circumference of the circle is 2 pi r, right. So, circumference of the loop is equal to 2 pi r. So, integration of dl is nothing but 2 pi into r, because r is the radius of this loop, is equal to mu naught into I. Okay. So, B is equal to mu naught into I divided by 2 pi r. So, this is the expression for magnetic field B at a point outside the conductor. You can consider the point here, you can consider the point here. On this loop, you can consider the point anywhere. So, all the points are at same distance from the axis. So, magnitude of magnetic field is constant. So, B is constant. dl is the line element. On adding all the line elements together, we get the whole loop, which is nothing but circumference of the circle. So, the magnetic field at a point outside the conductor, B is equal to mu naught into I divided by 2 pi r. So, from this expression we can write magnetic field is inversely proportional to r. Outside the conductor, magnetic field is inversely proportional to r. That means, as radius increases, strength of the magnetic field decreases. If the point is somewhere here, or if the point is here, then for this point r is more. As r increases, magnetic field decreases. So, at this point strength of the magnetic field is less compared to this point. So, magnetic field is inversely proportional to radius r. So, using Ampere Circuit Law, we can calculate the strength of the magnetic field at a point outside the conductor. Similarly, we can derive an equation for the magnetic field due to straight current carrying conductor at a point inside the conductor. So, this is how we can derive the expression for magnetic field outside the conductor. Now, let us see how to derive an equation for the magnetic field strength at a point inside the conductor. Inside the conductor. Again, consider one current carrying wire or the conductor. So, this is the conductor. This is the axis of the conductor and this is the radius, and radius is represented by A. So, this is A, this is also A. A is the radius. Now, let us consider one point P inside the conductor. For that, what we have to do? You have to consider one loop inside the conductor. So, this loop is nothing but Amperion loop. There also, in first case, we have drawn one circle or the loop outside the conductor. That loop is called as Amperion loop. Here this is the loop, Ampere's loop. At a point P, what is the magnetic field that we have to calculate? So, now the point P is inside the conductor. So, this is R. R is the distance between the point P and the axis. So, this is R. If you consider the point here, then this is R. If you consider the point P here, then this is R. So, R is same. So, consider a point P inside the conductor carrying current I. Let A be the radius of the wire or the conductor and R be the distance from point P to the axis of the wire or the conductor. Let I be the current flowing through this conductor. So, I is the current flowing through this conductor. But the Amperion loop is this one. So, this is I current through this whole conductor. But according to Ampere Circuital law, the line integral of B dot dl for a closed curve is mu naught times the current which is enclosed in the curve. The current enclosed in the curve is only this much. So, this is the current which is enclosed in the curve. Okay. So, this current is different from this current. I is the total current flowing through this conductor, but IE, I will denote it as IE. So, IE is a current passing through this curve. Okay. So, we need this current IE because this IE is not equal to this I. Let us find out circumference of the circle. So, circumference of the circle is equal to 2 pi r. Circumference of the circle is 2 pi r because r is the radius of the loop. So, circumference of the circle is equal to 2 pi r. Now, the current through the area is IE. Current through this area is IE. This is not equal to the total current I. So, then what is IE? How to calculate? Now, the current through this cross sectional area or the current flowing through this cross sectional area is I. So, area of the circle is pi r square. Here A is the radius. So, pi a square. Area of this circle is pi a square. So, area of this circle is pi r square. So, area of this circle is pi r square. Area of this big circle is pi a square. Now, current through the area pi a square is equal to I, right? Current flowing through this area, that is pi a square, is I. Current through the area pi r square is equal to. So, what is the current through this area? So, area of the circle is pi r square is equal to, that is IE. What is IE then? Cross multiplication. IE into pi a square is equal to I into pi r square, or IE is equal to I into pi r square divided by pi a square. So, IE is equal to pi cancels, I into r square divided by a square. So, this is the current enclosed in the loop. Okay. So, this IE is different from I. Now, according to Ampere's Circuital law, closed line integral B dot dl is equal to mu naught into I. Here I is nothing but IE. So, this current. So, closed line integral of B dot dl is equal to mu naught into IE is nothing but I into R square divided by A square. So, closed line integral B dot dl is equal to, B dot dl is nothing but B dl cos theta. If R is constant, then magnitude of magnetic field is also constant, taking that outside. Theta is 0, cos 0 is 1. So, dl is equal to mu naught into I R square divided by A square. So, we know that integration of dl is nothing but circumference of the circle. So, circumference of the circle is 2 pi r, which is equal to mu naught into I R square divided by A square. So, B is equal to mu naught I R square divided by A square into 2 pi r. So, r cancels, r and r. So, we get B is equal to mu naught by 2 pi I into r divided by A square, mu naught I r divided by 2 pi into A square. So, this is the expression for magnitude of magnetic field at a point P inside the conductor. From this equation, we can say that B is directly proportional to R. That is, inside the conductor, as R increases, magnetic field strength also increases. But outside the conductor, as R increases, magnetic field strength decreases. So, outside the conductor, magnetic field is inversely proportional to R, whereas inside the conductor, magnetic field is directly proportional to R. So, this is a basic difference between magnetic field at a point outside the conductor and inside the conductor. Okay. Now, let us see how to represent it graphically. So, this is the graph showing the variation of strength of the magnetic field, which is taken along y axis and with the distance r. So, we know that inside the conductor, so this is a conductor carrying current I. So, this is Amperion loop inside the conductor. So, this is R, this is the point B. So, this is outside the conductor, this is also R. So, this is A. Inside the conductor, as R increases, magnetic field B also increases till it reaches the point A, right. As R increases, B increases till it reaches this A, radius of the wire. Okay. So, this is the point A. So, from here to here, B is directly proportional to R. So, as B increases or as R increases, magnetic field B also increases, because B is directly proportional to R till it reaches A. So, up to this point. Outside the conductor, after A, what happens? As R increases, strength of the magnetic field decreases, right. So, as R increases, strength of the magnetic field decreases. That means, as R increases, B value decreases. So, this is the graph. So, here B is inversely proportional to R. Up to this point B is directly proportional to R, after this point B is inversely proportional to R.